Anyways, so let's start. Okay, is the screen visible?
Yes, sir.
Fine. So in the previous class, we discussed about the project, right? And before that, we had a revision of the module 2. So let's start off from where we have left, right? So we discussed earlier about this inductive bias. We formed a simple definition of a inductive bias and also which was actually a approximate definition, approximate inductive bias for ID3. And also we went ahead to discuss the uh, inductive bias with respect to ID3 using some examples, right? We saw, and we again defined a more closer approximation of the inductive bias of ID3, right? Which says that shorter trees are preferred over longer trees, and also that trees that place high information gain attributes close to the root node are preferred over those who are not close to the root node, right? So here is where we left. Now, moving further ahead with the inductive bias, as you can see, we have two basic types of inductive bias here: the restriction bias and the preference bias. Right. So, as the name suggests, the restriction bias put some kind of restrictions to the inductive bias, and preferences bias is the bias which is the inductive bias with some kind of preferences. Now, what are those? We will go into depth. So for that, let's consider this difference between what we have earlier, what we have discussed, like the hypothesis space search in these two different approaches that we have. One is the complete hypothesis space search, which ID3 makes use of, and one we have the incomplete hypothesis space search, which the candidate elimination algorithm we have seen in the virgin space of the candidate elimination algorithm. Right, so we have these two different approaches, and we have to see how this different inductive bias plays a role in these two different approaches. So in general, just to put it in a like introductory definition, you can say a basic definition, we can say in brief that the inductive bias for this ID3, the ID3 search hypothesis, it follows from its search strategy. If you remember, right, we have discussed how this ID3 hypothesis based search is conducted, right? It makes use of the search strategy. But whereas when we see this candidate elimination algorithm, the approach of this candidate elimination algorithm, it follows the form of the search space, right? Now the search strategy and the search space, what is the difference? In the candidate elimination algorithm, we made use of the virgin space, right? Uh, so the strategy there used, the method that was used there was the search space. But here in the ID3, we make use of the search strategy, right? Which actually searches the whole decision tree, right? If you can remember, we have discussed the various aspects of searching into the decision tree, right? Now, to discuss in more depth, just to give you more better idea, how can we say that ID3 makes use of this search strategy and candidate admission, which makes use of the search space search? How this inductive bias difference? What is the difference between the inductive bias by these two algorithms? Now, the inductive bias for ID3 is basically a preference bias, right? And with the candidate elimination algorithm, the inductive bias, the type of inductive bias that we have here is the restriction bias. Now, what is this preference and what is this restriction? Now, as you can see here, that for inductive bias, which is a preference. Now, what kind of preference is that? It is the preference for certain hypotheses. What kind of hypothesis? These are the certain hypotheses which has little preference. For example, let's say for shorter hypothesis, preference for some shorter hypothesis with no hard restrictions. There is no restriction. Now, what can be the restriction? If you can recall, when we discuss the hypothesis, right? Different types of hypothesis. Restrictions are nothing but the constraints, right? the few values which we are restricting it to. What values? The values for some attributes. For example, the previous algorithm, the previous example that we have taken, right? Playing tennis. So we have different attributes over there. Now, having restriction or constraints for the values of different attributes in that particular problem is kind of a restriction that we are trying to put here, right? But exactly opposite to it, the preferences, what it says that the IDT algorithm which makes use of the preferences of what? Preferences of shorter hypothesis with no hard restrictions, right? Which means no constraints on the hypothesis that can eventually be enumerated. Now, this particular form of bias, which is the preference bias, right, which is used by ID3, this preference bias is typically called a preference bias or alternatively a search bias. We also name it as a search bias. Now, I hope the example that I've given just now is clear. That is the decision tree. If you can recall, playing tennis, right? Uh, we had a decision tree. We had a root node. We have different attributes, right? One of the attributes was selected as the root node, and then we have other attributes which were actually the sub nodes, you can say. And then for each of those attributes, we had different values, right? For example, humidity, we had different values. For temperature, we had different values, right? For outlook, we had different values. For wind, we had different values. So having restrictions or having some constraints over these values for those attributes will create kind of a restriction, right? But in the preference bias, when we make use of the preference bias, which is a type of an inductive bias, we have no hard restrictions, right? And we are having the preference for more shorter hypothesis over all other hypotheses, right, which are available. So, hope this point is clear that how ID3 algorithm, which is nothing but the decision tree algorithm which we make use of, right? It is the example of a preference inductive bias, also called as a search bias. Now, on the other hand, the inductive bias, which is used by the candidate elimination algorithm, if you can recall the diagram that we have seen in the when we discussed candidate elimination algorithm, right? So we had a block diagram wherein we have candidate elimination algorithm, the new data set coming into it, the training data set, and also a type of inductive bias attached to it, which was giving a better accuracy uh, talking from the overall result point of view, right? So that was the bias that we have seen. But what kind of inductive bias was that? So candidate elimination algorithm basically it is in the form of a categorical restriction on the set of hypotheses, right? It is the form of a categorical restriction that we put on the set of hypotheses, right? So if you can recall, we discussed example of again playing tennis, right? So we had different attributes there, but we are trying to put some restrictions when we discuss this candidate elimination algorithm. We had tried to put some restrictions. Playing tennis is not an option, so result is no, right? So it's a restriction. So the inductive bias for this candidate elimination algorithm is in the form of restrictions, right? Restrictions on what? Restrictions on the set of hypotheses that we have. The complete set of hypotheses, which is capital H, you can recall, right? So this particular form of inductive bias, which is called as a restriction bias, is also known by the name of language bias, right? So when the question is asked, let's say the question in the examinations, if it is asked that please write a note on language bias. So don't get bogged down by this term language bias. It is nothing but it is same as the restriction bias, right? Why language bias? Language bias because, as I said, we are trying to put some restrictions here, which is nothing but a type of a grammar that we are trying to put here, right? We are defining something which is specific. It has to be like this only. Example, right? So that's why the name it has given. the 2 points, like what is the difference between the restriction bias as well as what is the preference bias is clear, right? Anybody, any doubt before moving ahead? Yeah. Okay, maybe we'll take the doubt clearing session at the end. Okay. Okay, so just to put it in a nutshell, now the question that arises is when to use or which one is better, preference bias or restriction bias, right? Because it has its own, you can say, merits and demerits, right? So preferences bias, the example that we have taken here is ID3, which uh, absolutely uses the preference bias, and the candidate elimination algorithm, which actually uses the restriction bias. But the question here is which is better, right? When to consider this preference bias or when to consider restriction bias, if at all we want to include the inductive bias into the algorithm, learning algorithm, right? So usually the most of the problems that we have here in machine learning, so considering the majority of the problem, typically the inductive bias that we prefer is the preferences bias, right? So preferences bias is more desirable than the restriction bias. Now, reason being, in simple terms, if I have to explain this, the preferences bias will give you, from the set of hypotheses, it will give you the important hypothesis or the hypothesis which can define majority the whole training data set, right? So it gives you the preferences that, okay, first you process these types of hypotheses and then you go for which are not so essential hypotheses, right? So it gives you kind of a preferences. But why not restrictions, restriction bias? Because restriction bias, what it will do is it will only give you the restricted uh, type of a hypothesis that we have to be processing. And in that process, what will happen is you can lose on some of the hypotheses which can be uh, very important enough while training a system, training a model, right? So we don't want to miss upon those hypotheses. So if we miss those hypotheses, we may miss the target function, right? We will not get the target function. But on the other hand, the preferences bias, apart from just the preferences set by the model, we are going to process the other hypothesis as well. So in that course, we may end up having some other hypotheses which were not in the preference, but they do play an important role in the overall training of a model, right? So that can lead to some other target functions as well, right? Some other they can lead to some other target functions which can be important from the training point of view, which restriction bias cannot give us that flexibility, right? So just to put it in a nutshell, we prefer preferences bias typically is more desirable than the restriction bias, right? And there are few other learning algorithms also which actually combine these two types of restriction in the inductive bias. Right? They combine both the preferences bias as well as the restriction bias for better accuracy or better holistic view of the inductive bias. Now the question again will arise that whether these both the types of inductive bias, preferences bias as well as restriction bias, can they be applied on a particular problem? Can they both be applied on a particular problem? So not there are not many type of problems which are available which can say that both the inductive bias can be applied on it. But there are very seldom problem statements which do have the flexibility to incorporate both these inductive bias, right? Preferences bias as well as restriction bias. So there are some learning systems which indeed combine both of these. Now, having been discussed so far, another question that arises in our mind is why this shorter hypothesis, or why these simpler hypotheses, right? Why to prefer this simpler hypothesis? Some may say that simple hypotheses are easier to process. We can cut down the timing, we can short down the code, we can reduce the processing time, or we can increase the ideal time of a system, right? If we process shorter hypotheses. But on the flip side, if we consider more complex hypotheses, we are having better analysis of the whole data set. We have better hypothesis which can tell us more about what type of training to be done, right? But at the cost of what? At the cost of lengthier code, more processing time, more storage, etc. Right. So both having their own pros and cons. So it becomes a topic of debate, like whether we should prefer shorter hypothesis or no, or we should instead go for a more complex hypothesis, right? But keeping in the mind that it is not the human that we are training the systems. So it has to be simpler, the simpler the better, right? So most of the data scientists, they land up saying that we do prefer shorter hypothesis than the complex hypothesis right away. So one such question which was raised by a few of the data scientists, and the the tentative answer was given by the William of Occam, which was popularly known as Occam's razor also. So he was fairly competitive enough to justify why we should prefer short hypothesis, right? So he says that prefer this simple hypothesis that fits the data. Okay, so according to him, which is that he termed as Occam's razor, he says that prefer the simplest hypothesis that fits the data, right? So one simple reason why uh, he would have come up to this conclusion is that if we, even though we have different types of hypotheses, but the hypothesis which can fit the data will give you more about the model, more information about the model, right? Let it be the simple one or complex one. So we can always start with the simple hypothesis which can fit the data, and as we proceed, we may uh, end up having a model which can process the complex hypothesis, and those complex hypotheses can also be said that they also fit the data completely, right? So, but his justification was we prefer, it is usually preferred to make use of the simplest hypothesis available from the set of hypotheses which actually fits the data. So that was called as it Occam's razor. Now there might be few questions arising in your mind, like again, like I said, why simplest hypothesis? What if the simplest hypothesis which we have in the set of hypotheses doesn't fit the data, and instead there are intermediate hypotheses or more complex hypotheses which are actually fitting the data? So it can be there can be argument for that, there can be discussion for that, but let us go ahead and discuss the different arguments that we have with respect to the statement made by the Occam's razor, right? So now this statement doesn't fit perfectly as well, right? It has its own problem, it has its own difficulty. Now what are those problems, what are those difficulties, right? So one of the problem is that one argument is that because there are fewer short hypotheses, right? From the all set of hypotheses, of course, when we search the hypothesis, you can see we will have very few short hypotheses, and mostly the hypothesis will be either medium sized hypothesis or mostly the complex. So the number or the quantity of the shorter hypothesis from the set of hypotheses that we have is actually very less, right? So that is one problem here, but that is not the actual problem. The actual problem is, let me define it uh, completely. That the argument here is that the fewer shorter hypotheses than the longer ones, right? The argument is that because there are fewer short hypotheses than the longer ones, now this is actually based on the straightforward combination argument, right? So it is just in simple terms, not any exceptionals in general, you can say. So since there are fewer shorter hypotheses than the usually longer ones. It is very less likely that the data scientist or anyone will find a shorter hypothesis coincidentally fits the training data, right? Right. So a simple probability, right? The less, for example, let's say you have a basket of fruits and you have different types of fruit, but you have very less apple. Let's say you have only two apple in the basket of 20 fruits. You have a basket in which you have 20 fruits, and out of that you have only two apples, and remaining are, let's say, oranges and bananas and other pineapple and so on and other fruits. So the probability of drawing apple is very less. Right? Similar is the case here. We have set of hypotheses and in which we know that we have very few shorter hypotheses. So it is very less likely that one will find a shorter hypothesis which coincidentally fits the training data, right? So I hope you get the point here. So that becomes a little difficult here. Now the actual difficulty here is that there are very small set of hypotheses which can actually define, right? And most of them are actually arcane. By arcane, I mean which are the hypotheses which are not so understandable by all, right? So not everybody can understand it. Very kind of a secret or not clearly understand. So the hypothesis from the all set of hypotheses that we have, first of all, we have very less hypotheses in numbers which are shorter compared to the longer ones, and at the same time there are few shorter hypotheses which are less understandable. We cannot understand the actual uh, what the hypothesis means. So that is one argument with respect to the uh, Occam's razor that Occam has put, that prefer the simplest hypothesis that fit the. Now the story doesn't end here. Right? We have other few more arguments which says that the problem here with the first argument again, the problem here, the second problem, first problem is, as I said, that there are very many small sets of hypotheses that one can define, and most of them are understandable, right? It cannot be easily understandable. Now there is one more problem with respect to this argument is that uh, the size of a hypothesis, right? The overall size. By now you must be already familiar with what do we mean by the size of hypothesis, right? Size of hypothesis is nothing but the number of values that we have in that particular hypothesis, the attribute values, right? So the size of hypothesis is determined by the particular representation. Now, what kind of representation? The representation which a particular learner makes. Learner is nothing but the training model here, right? So the size of the hypothesis The size of the hypothesis is determined by the particular representation which is used internally by the learner. Right? Now this representation, not this word here, it is internally by the learner. What internally? It is the internal representation. Now the problem with respect to this internal representation is that the two different learners using different internal representations. Right, let's say you have two different learners and they both use the internal representation. So since it is a internal representation, they could arrive at different hypotheses, right? Because the representation is internal to that particular learner, and for the other learner, it is again internal to itself. So the hypothesis which ultimately they are going to form might be different, right? So two learners using different internal representation could arrive at different hypotheses. So again, which result into the contrast, right? When we have two different hypotheses for the same model. Now, the another argument with respect to the Occam's razor that we discussed, which is again let me recall that is, it says that prefer the simplest hypothesis that fits the data. Okay, why I'm giving you this repeated definition is because this is very important, and this will tell you a lot of other things. What are the shortcomings of preferring a shorter hypothesis? What are the advantages also to prefer a simplest hypothesis? simplest as well as the shortest hypothesis. Now, another argument with respect to this Occam's razor is that it will produce two different hypotheses, like I said, right? So, the two different learners using uh, their own representations, which are internal to them, and which is as a result they are going to produce two different types of hypotheses again. So that is the argument that it will produce two different hypotheses from the same training data set, right? So for the same training examples, how come are we having two different hypotheses, right? So the key point here is because they have their own internal representation, right? The representation, the hypothesis representation, which is internal to itself, internal to the learner. Now, since they produce two different hypotheses from the same training example, when it is applied by two different learners, that perceives these examples in terms of different internal representations. Right? So I hope you got the point here that what are the shortcomings as well as what are the benefits of having this shorter hypothesis, or in general why do we prefer shorter hypothesis, right? So these arguments, I mean, they're still unanswered. They have to be discussed more. But we do have subsequent lectures, subsequent topics in the upcoming months, wherein we'll be discussing about these in detail. Right. So far, just keep in mind that this is the reason why we prefer shorter hypotheses over the longer ones, and the different arguments with respect to this Occam's razor is these arguments. Right. Now, having been discussed so far, there are a few other issues with respect to the decision tree learning algorithms as well, right? So, since these are upcoming algorithms, these are newly developed algorithms, there are a lot of issues, a lot of questions that need to be unanswered, and that is the reason that if you can observe, at the end of every topic, we are discussing what are the issues with respect to that particular topic or that particular algorithm, right? So when we discussed issues with respect to the fineness algorithm, we discussed issues with respect to candidate elimination algorithm, right? So we will discuss what are the different issues that we have here in the ID3 algorithm, which basically is the decision tree learning algorithm, right? So issues we will discuss in the next class, but before that, I would like to know from you guys any doubt or any question so far which is to be addressed again. Yeah, anybody. Okay, since yesterday also we didn't had much time remaining for the question answer session. So with respect to yesterday's lecture also, if you have any doubt regarding project or anything, you can ask now. I hope yesterday's session was also useful. The discussion that we had with respect to the different project topics, how can you go about selecting the project topic? What are the different important things that you have to take care while proceeding, while you do this project throughout your year, right? So I hope you have made note of whatever we have discussed yesterday, and you will be adhering to those instructions and follow having a follow up of those things. So if you have any doubts, you can ask with respect to anything, project or as well as this uh, lab or lecture. As far as lab is concerned, I've already told you about the how to write about the journal, what have to be submitted in the form of assignment, then how to go about it. I believe you must have already started off with installing the environment for that. So I prefer using a Jupyter notebook. So we will be carrying forward whatever the lab uh, programs in the Jupyter notebook. But I got few messages from few students that Jupyter notebook is not possible for us. Can we go for Google Colab? So that is also fine, especially those who don't have laptop with them right now. They can use Google Colab in their mobile, which is also fine, right? So please explore such tools, but uh, stick to these preparations. What we do here, don't miss out. Don't uh, procrastinate your work. And if you have any doubt with respect to lab or lecture, you can ask anytime. Yeah, please come up anybody, and if you are having any doubt, let that doubt be simple one, silly one, similar doubt others can have, right? So your question can be the same question which your friend has. No doubts? Yeah, quickly tell me. Okay, so if there are no doubts, that means you have understood everything. Good. So we'll see how do you write up your journals, your uh, how do you perform in your labs as well as in your eyes. That's fine. Okay, so if there are no doubts, we shall conclude the lecture here. You are free to leave the meeting. We shall meet in the next lecture.